So most of you in here know ALTER. We are a collection of companies in France, 2 here in Spain, and also in the UK. Between us, we offer a full service facility, everything from parts procurement through to assembly, certification, and of course testing. What we do in the UK is packaging. So we have a full range of capabilities. It seems to be a little bit hidden at the top, but wafer dicing, but we also offer die bonding, wire bonding, flip chip, optical alignments, all the way through to finishing a complete package and laser marking. We offer packaging as a service primarily for precision assembly, for photonic, and also for microelectronic devices. So we offer design, prototype, process development, as well as volume subcontract manufacturing, all the way through to flight module assembly. And we do this through mechanical, optical, thermal modeling, FEA, and high reliability package optimization. We specialize in high reliability, difficult environment, things like space, places where the cost of failure is far higher than the cost of the module itself. So packaging, why package? Well, you need a few things. You have to have electrical interconnection, of course. Thermal management, very important, particularly for actives. Mechanical support is needed for most applications. And generally, for photonic packages, you have to be able to get the light in and out. Whether you're doing free space, fiber, or on a PIC, there's got to be some way to couple into the fiber, usually fiber, sometimes free space too. And environmental protection as well. Quite often the package needs to be hermetic. Again, particularly if you've got an indium phosphide active, it has to be protected from the environment. So what's shown on the bottom there is just a cartoon showing that functionality. Sorry about the resolution on that one, but that's how it would look in reality. So there's quite a lot of different components there. Where's the PIC? There it is. So for a complete device, the PIC itself, in terms of volume and mass, is actually a really small part. Also often in terms of cost. So this is a number that gets quoted a great deal. Usually. Okay, sorry. Is it better?
Yeah.
Okay, thank you. So this is a number that gets quoted a lot. I hear it all the time. Usually by customers who want us to drop our price. 60 to 80% of the cost is the package, and that's true, but it's not just the package. It includes the material cost itself. Apart from the die, you've got the metal housing, the assembly. If there's a modulator, you've got an RF interface. RF connectors are very expensive. There's assembly time. Alignment. Again, fiber requires alignment, and this can be quite painstaking, difficult process. Test and yield. And all of these are highly variable depending on where you are in the process and what exactly are you doing. So here's another example. This is a package that we did for a customer a little while ago. If you wait to the end to do your testing and find out what your yield is, then the cost is very high. You want to be able to reduce all of these steps as early in the assembly as you can possibly get, because if the PIC fails at this point, or if anything fails at this point, it's extremely expensive. So it's important to test the die as early in the process as you can. So challenges with the packaging. The direction everything is moving in is increased functionality, increasing integration. That's inevitable. It brings a lot of advantages. It also, however, brings challenges with packaging. Things become more sophisticated. There are a lot more factors to consider. There's a lot more input and output, things like density and size. All of those make it much more difficult to do packaging. There's quite often, if you have a number of different optical paths, then you have to worry about multiple fibers, and the fibers are not always the same as each other. PM requires special processes. It has to be aligned. It's very difficult to make that. Power dissipation as well is a really important consideration. People talk a lot about the cost of the metal box. However, if you've got to do thermal management, there's really no other way. It's extremely difficult to do anything other than have a metal box. And particularly so when you've got a demanding power budget. So once you start integrating a number of DFBs into a single package, the amount of power you have to dissipate, that power's got to be taken out of that package somehow, and that also becomes a lot more difficult. And then for PICs particularly, photonics in general, it's true as well. There's an almost complete lack of standardization on package rules. Certain foundries do it better than others. HHI is very good. They have standard design rules. Others not so much. They will be highly customized. They basically will put a design through as their customer requires. Standardization from one foundry to another is almost non-existent, which means every time we get a different packaging challenge, it's a new concept. We have to look at it anew. We can't simply apply the same rules each time. And then prototype to volume is probably the biggest challenge. So why are people doing this? If it's so difficult, why bother? Because it's still better than an alternative, which is you can have free space optics inside. Try and integrate that. It's very large, it's very expensive, all the components are expensive. Or you can have a fiber-based option, a little better in some respects, not so good in others. PICs are still far and away the best way to go. And where we are today, cost and assembly time, size, weight, power, there are massive advantages to doing PICs over what the alternative is. So we've already made great strides, but if you compare, for example, with the microelectronic industry, we're still a very, very long way from standardization. We're still a very long way from being able to have any kind of automated volume process. There's a number of things that play into this. So die attach, electrical interconnect, fiber coupling, and also if you're doing indium phosphide and silicon nitride and polymer and any of this, there has to be a way to get the light from one of these to another. They have to speak to each other. While Guillermo was talking, I was hiding and unhiding this slide. Both Guillermo and Stefanos have gone through this in quite a bit of detail. You get the point. If you're generating light, you need indium phosphide, but you can't use it for everything. So die attach. Should be fairly simple, naively, but no. There's a number of factors you've got to consider when you're attaching a die to a PCB or to an interposer, to a ceramic. Two basic methods. You're either soldering it or you're gluing it. If you're gluing it, you've got to think about outgassing. If it's space or aerospace, you can't have an outgassing adhesive, particularly in a hermetic package. There are times when you need the flexibility of an epoxy. There are times when it has to be rigid, and therefore you want the solder approach. You've got to worry about the sensitivity of the die that you're attaching. So many of these active chips are sensitive to temperature, particularly if you're in the blue region, for example, gallium nitride. It's temperature sensitive. So if you're trying to solder it, you've got to be very careful about your temperature setting. And again, thermal properties. Solder generally is better for thermal conductivity than epoxy. There are other ways around it, but as a rule of thumb, that's generally true. And then again, the lack of standardization, quite often, sometimes, will get dye that just aren't suitable for packaging at all. And then you've got to start the design from the beginning. And then if you're integrating between indium phosphide, silicon nitride, some other kind of dye, there has to be very precise alignment in the position of the dye. And that means several things. It means your equipment needs to be expensive. Your processes have to be very carefully controlled. And it makes automation much more difficult. Yeah. And the last point there about die attach has to be considered as a whole. So you can't solve the die attach problem and then go look at the fiber attach problem. They're closely integrated. And that goes back to whether you need flexibility. If you're using microlens array, for example, you want to make sure it's very rigid so that you don't lose the alignment. However, if you've got an SVA, then that needs to be flexible so that, again, so that it will move as the fiber moves. So fiber coupling, a few people have mentioned mode field diameters. Typical mode field diameter on fiber, on a single mode fiber, is 10 microns. What you get from a PIC is generally 2 or 3 microns. So there has to be a way to couple those in. There's a number of different ways to bring fiber in. There's a lot of different fibers themselves. So the single mode, you've got multi-mode, and then even within that, you have lens fiber, where basically the manufacturer will put a lens and it's part of the fiber. They will attach it to the end of the fiber. Clear fiber, which is a more conventional approach, and of course FPA, which is what's shown there. Then when you come to attach it again, to attach fiber, you can have laser weld attach, which is favored for things like space where it has to be reliable. But there's also UV cure and others. Again, this requires complicated, expensive equipment and highly skilled operators. So some examples of fiber coupling. These are okay. So these are a few projects that we've worked on, just showing some different examples. There are 3 sort of main types. So edge coupling is what you would consider. So this is an example of an edge coupled device. We're bringing the fiber into the edge of the PIC. So you effectively you're butt coupling, or you can also do it by free space alignment, which gives you a direct connection between the fiber and the waveguide. That's well understood. It's a mature technology. It's something that works very well if you don't have a lot of fibers or a lot of ports. It does require very precise alignment tolerance. It's also not terribly scalable as it is, because it's got to be done on each individual device one at a time. FPA coupling is a variation on that. So fiber V-groove array coupling, if you've got multiple fibers, you can bring in sort of 8, 16, however many at a time. Similar comments apply for that. It's a little better for scalability, but not much. And then a little bit more promising is grating coupling, where you basically build a grating, a diffraction grating into the edge of the PIC, and that effectively does your mode field adaptation for you. It can be contact, which is what's shown here. It's usually vertical, as you can see from this one. There are some other ways to do it. So these are fixed. There's a free space version here, where effectively when you bring the fiber in, it doesn't physically, that's the PIC there, it doesn't physically contact the PIC at all. What you do is you cleave the end of the fiber at an angle, and then that will divert the light down and integrate onto the PIC there. And that brings its own challenges, but it solves some of the problems generated by the vertical alignment. So what do people use? Everything. Right, so this is, each line here is a project. And depending on the project, depending on the application, all of these methods get used. And sometimes multiple methods on a single device as well. Okay, so electrical interconnect. So you've got your die. That's attached now. How do you do the electrical interconnect bonding? Wire bonding is probably the most mature type. It's well understood. It's cheap if you're only doing a few, but it's very sensitive to the finished type and the quality, and it doesn't really fail. Gold ball bonding is more versatile. It's multi-directional. You can bond to different heights. It's also very good for sensitive dies because you don't have to actually touch the die with your tool. Wedge bonding is a finer pitch. It allows thicker wires and is therefore less sensitive to surface finish. But it's not vastly different to wire bonding in terms of how you do it. And then ribbon bonding is favored for applications where impedance is a concern, so for RF interactions, for example. But then flip chip is also, flip chip is becoming the method of choice for a lot of applications where it needs to be scalable, where you're concerned about RF speed. It also allows higher density of inputs and outputs. Any of these require high placement accuracy, so that you can align to the waveguide properly. Which one you choose really depends on the assembly, what you're doing, and what equipment you have available. So this is sometimes, often, what happens when you're trying to wire bond to an indium phosphide device. The metallization layers on indium phosphide don't always appear very well. It seems to be a particular problem with that material. Then you get peeling. So this one here, the bond lifted completely. There's a high density of attach on here, so this particular bond actually shorted. And in this case, the pad peeled off. So this is something that can happen. It's difficult to deal with because you can't assess until you try to bond whether that's going to happen or not. And then you've lost your die. What's happening is that as we go to smaller and smaller footprint sizes, things get more integrated. Track and bond pad dimensions are getting smaller and smaller. This is getting more and more dense. And that makes this problem much worse. So scalability. So here's a few examples. These are all PIC packaging projects that we've, well, that one's not complete yet, but that we've undertaken. A few things to notice about these. They're all different. I mean, they're all very different. These two are gold boxes. These two are, that is not. This one's not really packaged at all in terms of it doesn't have an enclosure. There's no standardization here. The other thing is that every single one of these is hand-built. This isn't scalable. We need standardized design rules would help a lot. Design for manufacturability as well. Any of these, we need to have these modeling tools to make it work at all when we get there. We can reduce the cost by using off-the-shelf packages, and we can build prototypes on production tool sets. All of these things help, but None of these, as we've shown them, they're not really amenable to scalability. So some more creative approaches. So fully integrated PICs, which have been discussed already as well. So what I would call special kits. So things like photonic wire bonds, 3D printed lenses. You have special processes, adiabatic coupling, passive alignment, and then hybrid approaches as well. Excuse me. Right. So fully integrated PIC. You can do it. Very expensive. Once you produce these chips, production is very scalable because you don't have to worry very much about input and output. You put this PIC into the package, you couple your fiber in, and you're finished. So you don't have to worry about attaching between different things. Your thermal management gets a lot easier. Your attach process gets a lot easier. Reliability is much better because there's fewer parts, so your fit rate goes down, and it allows standard microelectronic packages. So all of that helps to reduce the cost. However, it could take up to a year to produce one of these. It's very complicated. I think it's Stefanos or actually Guillermo went through all the different steps. You have to etch, you have to change it, you have to re-etch, you have to go through different material attach processes. So all of that takes a really long time. So the PIC itself, the die, is very expensive. And if it does fail, you've lost your entire device. Also, if you're doing all of this on one, you've got to use the same material, or you've got to use some combination. That means effectively you're compromising somewhere along the line. So you're not using the best materials for each process. Special kit. So this is wire bonding is kind of the flavor du jour, I think. It has a lot of appeal. It means basically the way it works is that you put down your individual components, so you can select the best components. You put them down on your carrier. You don't care all that much about the alignment. You can use fairly standard alignment techniques. They don't have to be high precision in terms of the placement. And then once they're down, you run it through the machine and it will draw these wire bonds through. And that means you automatically get your mode field adjustment, you get your alignment between the different components and the alignment to the fiber as well. So that all works really well. The problem with it is it's extremely expensive. It's about €1 million to buy one of these machines at the moment. That will come down, but for right now, that's where we are. It's fast compared to doing this by hand. It's not very bad, but you still have to do them one at a time. So it's not all that scalable. There's a variation on it where they effectively build these micro-optical elements on the die themselves. So this goes down, and then rather than putting in wire bonds, these micro-optical elements go in. It's like having a micro lens array, but you can customize it, and it's done inside the machine. It's all done in a single process. That I think is more promising because it allows you to test on wafer, for example, which you can't do with this. But again, you need the same machine to do it. So special processes, special pieces. There's a number of suggestions, a number of things that are being tried. So passive alignment, adiabatic coupling, 3D alignment, what all of these have in common is it allows you to alternate because they're not one at a time. There's something that you can put through. You can simply, once you've got it right, you can put it through a process. So there's a number of different ways. This is an adiabatic coupling approach. IBM are doing a lot of work on this kind of thing. Effectively, you've got V-grooves designed into the PIC itself. You bring the fiber in, and they will align into the V-groove. When things go wrong, they align perfectly into the V-groove, and then you fix it in place. You can do that inside the machine. It works very well, but it requires high precision. An alternative is a similar idea, but you're doing it free space with a micro lens array. So in this case, rather than physically aligning the fibers into the V groove, you're focusing them on the correct points, and also you can adjust the mode field using a micro lens array, so that can go in. This is a tapered waveguide idea, so this is doing your mode field adaptation here as well. This is compatible with the PIC, this then is compatible with fiber, and that also works quite well. And for actives particularly, this is an approach that looks very promising. So effectively what's happening here is that this is 3D alignment. So you actually etch your chip so that it has a physical well in it. And so after your silicon substrate, you've got all of your beam steering and everything else that you need, your interaction with your fiber, and then you can bring your active in and it fits into the fiducials and it will bond itself into the hybrid approaches. This is an HHI die. Hybrid approaches look really promising as well. The optical circuit is done in silicon nitride or whatever, and then you etch the alignment or the location features, and you bring your actives in. This is also related to the 3D alignment that we were just talking about. And then you can bring it in afterwards. Again, all of this can be done in an automated way. So this is also very promising. And you can optimize your components. You can choose the right material for the functionality that you need. No matter what approach you use, whether it's 3D alignment, whether it's a hybrid approach, you've still got to bring the fiber in. If you've got a fiber approach, and that's problematic and will probably remain problematic. On-wafer testing is really important to reduce the cost, not only the die, but you want to basically get that failure as far down the supply chain as you can, as early in the process as you can. Because by the time you've got the package, you've thrown away a lot of money. The PIC is a relatively small portion of the cost. Standardization of interfaces, processes, design. This is a lesson learned from the microelectronic industry. They put a lot of effort a couple of decades ago into bringing all of this down, and the way it was done was by standardization. These devices, they compete very well right now with free space, and they compete very well with fiber, but they're going to have to, when you're talking about quantum computing, for example, they're going to have to compete with microelectronics, which are far and away cheaper. And if you're talking about communication, they've got to compete with telecom standard toaster roaster kind of things, which again, what those two approaches have in common is that they were cost reduced by standardization. So in terms of how you couple fiber in, edge coupling is what's most commonly done today. It's a mature technology. It is consistent with semiconductor laser coupling, edge emitters. It has advantages. It's quite forgiving in terms of the bandwidth and polarization. So all of that is good, but you can't do on-wafer testing. It's got problems to do with the PIC design, and it requires active coupling and high precision alignment. It's not a scalable process. Vertical coupling is much more challenging at this stage, but it has a lot of appeal. So it allows this wafer scale characterization and testing. It does give you for layout flexibility and scalability, and is less sensitive to alignment tolerance. But it's not a magic bullet. It does have bandwidth and polarization issues. So there are going to be times when you can't use it.
Thank you very much. We have time for questions. Any questions in the room?
Thank you very much for your interesting talk. And I was wondering,
Actually, you have developed yourself packaging development kit to help, because one of the problems that when you design a photonic integrated circuit, actually you need to think as well how you are going to assemble it and test it. And one of the problems is that in our chips we need so many easy access lines, so many RF lines, and maybe we think too late. Where in the package you can do all this?
Yes.
And do you have a set of packaging guidelines that is available?
We don't, okay, so we don't have a formal PDK, but we have developed with the Tyndall and with the Euro practice, we have a set of design rules which we could share. One thing I didn't mention and meant to is that exactly your point is that co-development is really important. You can't design a PIC and then go and look for a package. You have to have the package in mind when the PIC is being designed, and that needs to be very cooperative. And especially as PICs develop further and become more complex and require, as you say, like higher density and more functionality and more thermal management, all of those things mean that the cooperation between the packager and the PIC designer becomes more and more important. And that is something that we're looking to continue and to develop more.
Another question is, do you take the PICs from indium phosphide and assemble from there, or do you expect them to come in already assembled in a substrate, which is the substrate you usually prefer to mount the chip?
Whatever customers want in terms of what we get. We may get a bare die, we may get die on carrier. That's up to the customer. We can deal with either one. Normally we'd use aluminum nitride, but sometimes there are reasons when that's not suitable and you have to use something else, and that's something that we can also deal with.
Okay, thank you very much. Any other questions? Thank you.
Desarrollo asked the student that would a more advanced PEOL for Innovación or an hybrid Innovación on the platform is the packaging?
I'm sorry, I don't understand the question.
Yes, that would a more advanced PEOL for InP for an hybrid or silicon platform is the packaging?
That's it?
Yeah.
Sorry. Okay, so what means I didn't understand.
Okay. Sorry. Good one.
It depends what you mean by more advanced. That means different things to different people. In principle, yes, but more advanced could also mean much higher density, and that makes things more difficult. Packaging gets easier if things are more standard. And if the packaging, the biggest issue is that when PICs are designed, packaging is not considered, or it's only considered at the end. So that's really where packaging gets easier. There are a number of things like, so this hybrid integration approach definitely makes packaging easier. But there are some advances that don't as well. I hope that answered the question.
Okay.
Thank you, Mr. Speaker again.